Chapter 3, Decisions Part 3. Lexicographic order roughly means dictionary order, so when we're comparing strings, we can compare them one character at a time using the compare to method from the string class. So if we say string 1, assuming string 1 is a string variable and so is string 2, we can say string 1 dot compare to string 2 less than 0. And what that means is that string 1 is lexicographically before string 2. If string 1 dot compare to string 2 is greater than 0, that means lexicographically string 1 would come after string 2. And then if the two strings are equal, if they are the same exact strings, then the compare to method will return 0. So what you need to know about lexicographic order is this is based on the ASCII table, which you can find in Appendix A of your textbook. The ASCII table is a subset of the Unicode table, which is every single character on every single keyboard on the planet, and we're interested in the letters A through Z, both uppercase and lowercase. Know that all uppercase letters come before lowercase. In fact, as a frame of reference, uppercase A has the decimal value of 65. A space comes before all other printable characters. So if you have a space, it's going to be less than any letter that you have in your string. And the digits 0 through 9 also come before the letters. That's useful to keep in mind. So see Appendix A for more information about the ASCII table. So, implementing an if statement. If we want to decide on we need to decide on a branching condition, like original price less than 128. So we're deciding what is it that we're going to set up as our Boolean expression. And then we want to write some pseudocodes. What are we going to do if that's true? And then write some pseudocode. What are we going to do if that's false? And then double check our relational operators. So you're going to test with values at, below, and above the comparison. So if our comparison is 128, we want to make sure we test 127, 128, and 129. And validate, by hand, validate that the results we're getting are the results that we expect. So then we want, after we double check that we're forming this logically correctly, we want to remove any duplication. So discounted price equals blank times original price. We've got that expression twice, once with the true branch and once with the false branch. So it might be useful for us to set a variable as a result of the true branch or the false branch and then do our equation following that if statement. But then we want to test both branches and we want to write the code in Java. So here's an implemented example. The University Bookstore has a kilobyte day sale every October 24th, giving an 8% discount to all computer accessory purchases if the price is less than $128, and a 16% discount if the price is at least $128. If you know your multiples of 2, you'll know how magic these numbers are. If original price is less than 128, our discount rate is 0.92. Else, our discount rate is 0.84. Our discounted price is going to be our discount rate times the original price. Notice that statement follows the if construct. Multiple alternatives. What if we have more than 2 branches? What if we want to model the Richter scale, for example, where we want to know the effect of an earthquake? According to the Richter scale, if the earthquake has a value of 8.0 or greater, most structures will fall. That actually isn't true anymore given modern building codes, but this is the way it used to be. And then if it's between 7 and 8, many buildings will be destroyed. If it's between 6 and 7, many buildings considerably damaged and some collapse. And if it's between 4.5 and 6, there's damage to poorly constructed buildings. When using multiple if statements, test the general conditions after the more specific conditions, because we want to try to minimize comparisons, so we try to get as specific as possible first and then work our way to the more general. Here's an example of what that flowchart might look like. If the Richter value is greater than 8.0, we go to the true branch, most structures fall. Else, we go to the false branch and we test, is it greater than or equal to 7.0? And we don't have to say greater than or equal to 7.0 and less than or equal to 8.0 because we already know that it's less than or equal to 8.0. If it wasn't, we would have already gone on the true branch. So we're not asking questions that we already know the answers to. So if greater than or equal to 7.0, we go to the true branch, many buildings destroyed. If that's not true, we go down and test, is it greater than or equal to 6.0? And then if that's false, we go down and test, is it greater than or equal to 4.5? If that's false, we know there's no destruction of buildings. At this point, we know the value on the Richter scale is not significant, and so we just say no destruction of buildings. We don't need to test that it's less than 4.5 because when we get to no destruction of buildings, there is no other option that that value could be but less than 4.5. Here's what that might look like in an if structure. Hit the pause button for a moment and take a look at this code. I'd like to point out at the very bottom, unfortunately, the closing brace is cut off, so that at the very, very bottom there would be one more closing brace that would be shown. Also notice, because of the font used in this image, the code wraps around where you wouldn't want that to happen. You'll notice that that happens if you cross over what I call the red line of doom, the 80th character. But here it was just a circumstance based on this font size. So take a look at what's wrong with this code. Can you tell what's wrong with this code? Let's assume that our value on the Richter scale is 9.0, which is a very significant earthquake. If it's 9.0, what would be output? Most structures fall, many buildings destroyed, many buildings damaged, some collapse, and damage to poorly constructed buildings. All of that would be displayed, when in fact we only want most structures fall to be displayed. Why would that happen? Do you notice that those else statements are missing? Those are very, very important from preventing us from executing statements that are no longer relevant. So we don't want to print many buildings destroyed if it's true that the Richter scale is greater than or equal to 8.0. So we need those else's in there. Another way to do a multi-way branch is by using a switch statement. For those of you who are in or have taken AP Computer Science A, I should point out that the switch statement is not part of the AP subset, so you can skip this section. With the switch statement, it's based on an integer value, in this case some digit, and we have the keyword switch followed by that integer variable. And what it's doing is it's comparing that integer variable with each of these successive cases. So if that digit equals 1, as in case 1, we set digit name equal to 1. And then notice that keyword break. Break means stop the switch statement. Don't go executing the rest of the cases. We need that break statement. Otherwise, when our digit is 1, digit name would be 1, it would be 2, it would be 3, it would be 4, it would be 5, it would be 6, it would be 7, it would be 8, it would be 9, it would be the, yeah, it wouldn't go to the default, sorry. So we need to make sure that the break statement follows each of the statements we do as a result of the case before the next case statement.